So you remember in the last lecture I talked about the different kind of measurements, that we can have individual measurements and population measurements. And today I'd like to start on the individual side. So imagine we have individuals which move about and we can really follow their track. And we know the speed, we know the turning angles, we know the turning rates and all that kind of stuff. But first I do this in one dimension. So meaning that I have cells which only move left or right, or individuals moving left or right. So one application would be like microtubules in a cell. You know, a cell is made out of cytoskeleton, and part of it are microtubules, which are very elongated proteins. And then along the microtubules you can transport other proteins. And so they can go up or down, but nowhere else. So that would be a typical one-dimensional situation. And so there would be two correlated random walk. In one dimension. So 2.1 is the Goldstein-Katz model. Goldstein and Katz model for correlated random walk in 1D, and here I start right away with the PDE. So everything I do today is basically right on the PDE level, and then how the speed and the turning rate enters the PDE you will see very quickly. Before I do this, just give you some references. So this was first considered by Taylor in 1920. So it's relatively old. Fürth also in 1920. Then by Goldstein in 51 and Katz in 56. Okay. So we have two population densities, U plus of xt and U minus of xt. And then, of course, plus indicating cells which move to the right, and minus indicating cells moving to the left. So, so let's see. That's the density of right-moving particles. And then the other one is the density of left-moving particles. And now I would like to write down a PDE for their movement and for their change of direction. And yeah, since we are all experts in PDEs, I can use a transport equation to describe movement in one direction. So then, for example, I do a U plus t plus gamma U plus x. If I would write down 0, so don't write down the 0 yet, it will change. But if I would write down 0, then this is just movement to the right with the speed gamma. Right, so gamma is a particle speed. It comes right in there, and then cells move to the right. Okay. And then for the left moving, I have U minus t minus gamma U minus x is 0. Of course, it's not 0. If it were 0, then these are the left moving particles. But now they can switch direction. They can move, if they switch direction from plus, then they go minus. And if they have been minus, then they go plus. And so I have a transition rate, which I call mu over 2. So let's say the right moving particle changes direction with the rate mu half, and then it comes back as a left moving particle, U plus. And then left moving particles can change direction with the rate mu half, and they come back as right moving particles here, mu half U minus. Now you wonder maybe about this 1/2 in there, so you could call this mu. Why not, right? It turns out later it is kind of simpler to have the 2 in here, and then later it disappears. Otherwise, we're not using the 2, but then later we have to carry a 2 around all the time. So, so here gamma is the particle speed. And mu half is the turning rate. So rate of switch from left to right or right to left, or reverse. Yeah. Okay, so this is a hyperbolic PDE, right? A system of two hyperbolic PDEs. But the hyperbolic part is linear, so there's no problem here. And then it's coupled by these transition rates mu. So very simple. And this is known as the Goldstein-Katz model for correlated random walk in one dimension. Now I will show you now a sequence of more or less equivalent transformation of the system. And they're all in their own right are studied in science, and they're all interesting from various point of view. So maybe a first equivalent formulation would be this: u plus t plus gamma u plus x. And I just write down the formulation, and then you see very quickly that these are equivalent. So I write this as minus mu u plus mu half u plus u minus. Okay, so I basically took the mu half u plus. If I work it in with the minus mu from here, I get minus mu half, and then this is the first equation. And in the other case, I have u minus t minus gamma u minus x is minus mu u minus plus mu half u plus u minus. So same story. Now I do this because this is a formulation I will generalize later if I go in higher dimension. So in higher dimensions, this is actually straightforwardly generalized, but this is not. And the reason is just because of the meaning. So here what it means is I have a particle moving to the right. It changes direction with the rate mu, but then as a new direction it chooses either way with 50% probability. So half of them go to the right and half of them go to the left. And that's why you have the mu half here. And then a left moving particle changes direction, or maybe just stops, and then one half goes here and one half goes here. So that's how the system works. So then you have the change of direction going out of this and choosing a new direction as described on that side. Okay. So let's introduce new variables. As the total population density, total population, which is u plus u minus. And then another variable for the difference. But now the difference I multiply with the speed, and then together it will be a population flux. Population flux, which I call v, and this is gamma times u plus minus u minus. Okay. Then what I can do with these equations, where I can add them up and I can subtract them, and then I get a system for u and v. So that's very easily done. Maybe don't waste too much time. So if you add these equations, for example, you get u plus t plus u minus t, which is ut. And then you add this flow term, but you get gamma u plus x minus gamma u minus x. So you have minus vx. And there you see why I smuggle in this factor gamma, so that together it will just be the v. And if you add these two equations, it's easier now to do it on this formulation. If you add these terms, it's a 0, and if you add these terms, it's a 0. So the right-hand side is 0. Okay, so you get a very typical, very classical conservation law. It's just a conservation law. Something is transported by a velocity field v. So this is a conservation law. And then similarly, we can get a law for the velocity. So we build the difference of the two equations, but also we multiply with gamma. So we do gamma this minus gamma that. Then we have vt here. Here we get the minus sign becomes a plus sign. So we get gamma square plus gamma square ux. Oh yeah, and with my conservation law, this must be a plus. I'm sorry. I just have a little typo. So plus uxx. No, what am I doing? This comes later. So ux. And then on the right-hand side, I do the difference. So now it's easier to use this formulation here, because this term cancels if I do minus. But this term survives, and you get u plus minus u minus with the mu and the gamma and so on. So this is minus mu v. Minus mu v. So then this is the law for the velocity, which depends on the total population u as derivative. Okay. So now this guy is known as a Cattaneo system. Cattaneo system. And there's a wonderful paper by Luigi Preziosi and Joseph Preziosi, 1988, where they talk about these Cattaneo systems. Now, Cattaneo was an Italian scientist, and he wrote down this model in 1948, I think. 1948, in the context of heat transport. So this model was derived for heat transport in media with memory. So specific media. So this is heat transport with memory. So that's a pretty cool relation. I mean, these are equivalent formulations, right? I started with the model for cell movement. I come up with a model for heat transport in media with memory. So mathematically they're equivalent, but of course physically they're very different processes which are modeled. So I think that's cool. But that's not all of it. Let's see. So we can do a few more modifications. Just need to see how I organize my table, my things here. Okay. Now I differentiate this again. I differentiate these equations. The first one by time, the second one by x. And I would like to throw out one variable and get an equation for u alone. But then it will be higher order. It will be a second equation for u. Second order equation for u. So I differentiate. First equation I differentiate by time, and I get utt plus vxt is equal to 0. And I would like to replace the vxt from here, so I differentiate this equation by x. Okay, so I differentiate that by x. vtx plus gamma square uxx is minus mu vx. The minus sign here. And then I assume it's a formal derivation. I assume I can flip the order of differentiation. So let's say everything is C2. So then I can sub in Vxt for Vtx. And then also the Vx here, from this equation, from the first equation, Vx is minus ut. Okay, so Vx is minus ut. So this goes in here. Okay, so let's do all this. Let's see what we get. So then we get utt. And so then vtx is minus gamma square uxx. Minus mu, and vx is minus ut is equal to 0. So I hope I get all the signs correctly. So then now I move the terms about and I divide by mu. I write 1 over mu utt plus ut equals gamma square divided by mu uxx. Okay. So I managed to get rid of v, but I have to pay with an order in the differential equation. So I have second order equation, but now it depends only on u. And now this transformation is no longer equivalent because I differentiated, but it's equivalent modulo a constant. So for the v term we can add a constant, and then the systems are equivalent. Now this equation is also known. This is the Telegraph equation. Now the Telegraph equation has a very interesting story as well. It has to do with the first transatlantic cable, which was laid from Ireland to Canada to transport signals through the Atlantic through a cable. And then the first cable, which they laid in about 1858 or something, Just see here my notes. So the first cable, 1858, was basically just a long cable. It was pretty heavy, and they put it into the Atlantic Ocean, and then it broke, and they had to fix it, and then it broke, and they had to fix it. So it was a huge effort, but eventually they connected to Canada, and they were able to transmit a few signals back and forth using Morse code. But the signal was very noisy. It was very difficult to send anything useful. And so they cranked up the voltage. They made stronger and stronger voltage, and at some point they burned out the cable. So, so then it was, after two weeks or 3 weeks, it was completely useless. So then a few years later, in 1860, Heaviside came up, and that's the same Heaviside from the Heaviside function. And he looked at a system of 2 wires which are close together, and then by the inductivity between the 2 wires you have a much less resistance, and the signal should be more clear if you use 2 wires instead of 1. And this is described exactly by the Telegraph Equation. So Heaviside came up with the Telegraph Equation, and he could show that this here transports an electric signal much better than the just one cable. And this is what they did in 1860, or in 1866. So then they built this cable, which was now double as heavy as the original one. It is a huge enterprise. So they got the biggest ship they could find. And the biggest ship was the SS Great Eastern. It was a steam boat with 5 steam chimneys. It was the biggest ship in the world at that time. And so they redesigned it just to lay out the cable. And then they laid out the cable over the Atlantic. And they used this ship also to maintain the cable and to fix problems. And then with this cable, they were indeed able to to maintain connection between the continents, between Ireland and Canada. So a very cool story, I think. All right. So then one final step. So I'm sure somebody's itching already that you see a diffusion equation here, right? So if mu is really big, then this term is gone, and then maybe this is a diffusion coefficient, so it looks like a diffusion equation right here already. So let's do this final step too. So then, so consider a limit gamma and mu to infinity. So meaning that, going back to the species, so the particles become very, very fast, gamma goes to infinity, but they also change direction very, very often. So they oscillate about. And this sounds like Brownian motion to me. And again, in the scaling limits, we have many choices how to do this, and it tells us exactly how we have to do this. So we want to keep this term. So gamma square over mu converges to a bounded value d. And so in this limit, then I get the diffusion equation. So we obtain the diffusion equation, which is ut equals duxx. Yeah, but now this is super cool. So this, I'm always excited if I can present this relation. So we touched so many things in science, right? All with one equation. So we started with the cells, moving here. We come to heat transport in media with memory. We have a relation to a transatlantic cable and the telegraph equation, and then finally come back down to the diffusion equation. So each object is interesting on their own right, and they have very different physical properties, but mathematically they all fit into this framework here. So that's cool. Now let's look at the boundary conditions. Boundary conditions for, let's look at equation 1, so the first system I had here. I have a PDE, now I have a finite domain, let's say 0 to L, and I would like to do the classical things like Dirichlet and Neumann and periodic boundary conditions. So on an interval 0L. So let's start with the Dirichlet case. boundary conditions. Yeah, directly boundary conditions for PDEs. So if I tell this to a student, for example, or to a colleague, they would just write down u at 0t is 0 and u at lt is 0. So don't write this. Don't write this. Nobody write this. So then everybody who knows something about hyperbolic differential equations, like my colleague over there, he would just jump out and leave the room in protest or throw tomatoes at me. So something is wrong with this. So this doesn't work. So why does this not work? Let's look at it. So first of all, now we can write it. So if I would assume ut0, u at 0t is equal to 0, this also means it's the sum of u plus u minus. Okay. And now these are population densities, so they're non-negative. And if the sum is 0, then each one of them is 0. So this would apply u plus at 0t is 0 and u minus at 0t is 0. Okay? And now one of them doesn't make sense. So which one doesn't make sense? You say u minus doesn't make sense. That is correct. And the reason is the characteristics. So if you look at the hyperbolic PDEs, you have to look at the characteristics. Right? So let's do that. So let's maybe plot my domain here. This is 0 to L, and this is time. And plot some of the characteristics. So let's start with the u plus equation. So we have u plus t plus gamma u plus x. So the characteristics is gamma t, and gamma is positive. So these are straight lines with slope gamma. So characteristics look like this. Like here, and like here, and like here. Okay? And then, of course, on this side of the boundary, the characteristics come in like this. So this would be u plus. And so where the characteristics are pointing into the domain, I can give boundary conditions. So I can say my solution is 0 here, okay, and then the 0 is transported inside. Perfectly fine. However, I cannot do the same on this side, right? The characteristic for u plus goes like this. And I cannot say this is 0 because maybe there was a different value here, which is transported to this boundary. So I can only give boundary conditions on the inward pointing characteristics. Okay. So to make this precise, I define something which I call the hyperbolic boundary. So this is then, so let's say omega t, so the domain we are interested in is 0 to L times 0 to t. And then the boundary of this, which I call the hyperbolic boundary, is delta plus omega t union delta minus omega t, where now delta plus is a part of the boundary where I give side conditions for u plus. Delta minus is a part of the boundary condition for u minus. And instead of writing it down, I just maybe plot this. So then this bit here is delta plus omega t, and then this bit here is delta minus omega t. And so then on the white outline I can give boundary conditions for the inward pointing characteristics, and on the red bit I give boundary conditions which go to the left. So this would be u minus and this would be u plus. Okay, so u minus can be given on the red bit and u plus can be given on the white lines. And together this is then the full boundary of the domain. Okay. So this is 0 to L. So meaning u plus of xt needs side conditions on delta plus omega t and u minus on delta minus omega t. So then if you look at time is 0 at the base, so both functions need to be given at the base, and this is the initial condition, so that makes complete sense. So at t is 0, we have initial conditions. So then we have u plus at x0 is a function u0 plus, and u minus is a function u0 minus. So that's good. Now where is...
Shouldn't we use capital?
Absolutely, yeah, we should use a capital T, so we fix the time in the beginning. Thank you. So let's do that here, right? So then this is the time where we go. Of course, it's a linear system, so it exists for infinity. There's no problem with that. But yeah. Okay. So then back to the question. So what are the right Dirichlet conditions? So these conditions I wrote down didn't work. So this didn't work. So let's ask the biology. So what does the Dirichlet condition describe? So if you look at the heat equation, where's the heat equation? Here's the heat equation. So if I look at Dirichlet conditions here, it means I fix the temperature on the sides. Let's say 0, so I fix it for 0 degrees, and that's it. Now for the Dirichlet condition here, it just means that on the side, that no particle can enter from the side of the domain. So u plus on the left boundary is 0, u minus on the right boundary is 0. So no particles can come in. So let's write correct Dirichlet conditions. They are then u plus at 0t is 0, and u minus at lt is 0. So they look a bit different than the classical Dirichlet conditions just because of what I explained. How about the Neumann boundary conditions? Neumann boundary conditions usually mean ux on the boundary is 0, right? The derivative is 0. But for the heat equation, ux is a flux. Ux is a population flux, so it means there's no flux to the boundary. But we do have a variable for the flux right here. So here I called it population flux is v. So it kind of makes sense to assume v is 0 at the boundary, so then you have no flux going through. But then v involves u plus and u minus, and on the left side I can only stipulate what u plus is. So I have to see it in the right way. So the idea is v is 0, and then I write this as u plus at 0t is given by u minus at 0t, and u minus at lt is given by u plus at lt. So these are perfect reflection conditions. So if a particle going to the left hits the boundary, it's reflected and comes back to the right. If a particle going to the right hits the boundary, it is reflected and comes back as a u minus particle. So that's reflection. And then finally we can do the periodic case, and the periodic case is exactly the way you would expect it. So basically whatever leaves on this side will come back in on this side. Whatever leaves on the left comes back on the right. So I don't even need to write it down. So the periodic case is actually easy. The other two cases are a little bit more interesting. Okay. And there could be a compatibility condition. So what he means is a condition here. Okay, at this point, from here you give the initial condition, and coming from the top you give a boundary condition on the side. So often you assume that it is compatible, so it has the same limit coming from the top and coming from the side. If it is not, then you have a shock which forms, and then the shock is transported inside, coming from 0. Okay. Other questions? about that. Okay, so so I did a lot of formal derivations and these boundary conditions. So now you can build a theory for this where you get existence, uniqueness, global existence, all of this. You can also formalize the limits which you make so that everything converges to whatever you claim. And I did this in one of my papers in CamQ, Canadian Applied Math Quarterly, 2010. But I will not go into any of the details here. I rather would like to talk a bit more about applications now. So, in what kind of settings do these models have been applied? And one application here would be correlated random walk plus reactions. So, what if we have, let's say, logistic growth? So the cells grow while they move around. And so how do we include a growth function into these kind of models? And this has been spearheaded by Karl Hardeler, who is my former supervisor, and myself. I've worked on this also a lot. So let's write this down. So we have u plus t plus gamma u plus x is mu over 2 u plus minus mu over 2 u minus t minus gamma u minus x is mu half. So which is which? This is minus, this is plus, minus u minus. Okay. And now there are several ways to do this. The simplest way is to assume each newborn particle chooses either direction with the same probability. So a newborn particle, it goes either right or left with 50%. So meaning if I have a function f, then half of it goes to the first equation and one half of it goes to the other equation. Okay, so f is the reaction part, and then half goes right and half goes left. Of course, we could do more complicated things so that if the mother goes to the right, then the daughter is likely to go to the right, etc. But let's look at the simplest case, because now I would like you to get to work. So I would like you to do all this what I did there on the left. So take a piece of paper, take your notepad and a pen, and you derive me the reaction Cattaneo equations and the reaction Telegraph equation, and then do the limit and see what you get for the diffusion limit. So let me write down what I like you to do. Okay. So A, find an equivalent reaction Cattaneo system. And then B, find a reaction Telegraph equation. And then C, find the diffusion limit. And so how much time do I give you? Maybe about 10 minutes or so to figure all this out. So find the equivalent reaction Cattaneo system. So we just need to find an equation for u and v. So we add the equations and we subtract the equations. If you subtract the equation, then the f term disappears, right? And so we get the same as before. If we add the equations, then the 1/2 f plus 1/2 f is 1f. So the Cattaneo problem is easy. So we have ut plus vx equals f of u, and then vt plus gamma square ux equals minus mu v. This is unchanged, right? And then to get to the telegraph equation, you need to differentiate this stuff once more. So you differentiate this by time, and so then you get f prime times ut. But then this term is the same as before. So this is a little bit more writing, and then what you get is what you get. So which one do we take? Maybe this formulation. So then you get 1 over mu utt plus, what do I have? Gamma square over mu ut. No. Sorry, I have to write it this way. So 1 over gamma square utt minus uxx plus 2 mu over gamma square ut equals 1 over gamma square f prime at ut plus 2 mu over gamma square f of u. This is not the most smart notation, so I really want to multiply by gamma square divided by mu, or 2 mu. Oh, I confused myself. Okay, so there's no 2. So I got it. There's no 2. Okay, if I multiply this, then I have 1 over mu utt, and then maybe this term plus ut equals gamma square over mu uxx, and then this term is 1 over mu f prime of u ut plus f of u. Yeah, so that's better. So then we can clearly see we got these additional terms from compared to before. And now as we, well, so that's the reaction telegraph. Graph equation. And now if we do the limit as gamma goes to infinity and mu goes to infinity, then this term vanishes, and this goes to d, and this term vanishes. And so what we get is the reaction diffusion equation. Ut equals duxx plus f of u. And now Dr. Matano is happy because his favorite equation just came out of this study here. Okay, so it kind of all makes sense. So we put in reactions and we know what they should describe, and they come out exactly the right way where we wanted to. So reaction diffusion equation. Okay. Yeah, so then you can ask, Dr. Matano is talking about traveling waves for this, right? So are there traveling waves for this? So, I mean, apparently they're very, very close. There's just one scaling limit happening. So are there traveling wave solutions for this? And the answer is yes. And the result is basically the same. So there's a minimum wave speed. If f is monostable, there's a minimum wave speed. And we have wave speed for c larger than c star up to gamma. So here we have a maximum speed gamma. And the wave can actually not be faster than the particles, right? So then there's a maximum as well. So traveling waves for reaction random walk problems. This was done by Schwedlik and Hadler. In a series of papers, this one. So, okay. Let's see, timing is perfect. I'm too unorganized with my papers. I would like to come back to the problem of the boundary conditions. So what we did here, we have the boundary conditions Dirichlet and Neumann for the hyperbolic model, but we also have a limit which leads to the diffusion limit. So now I would like to look at the boundary conditions in the limit. What do we get in the limit? And maybe I can do this right here. And where is my notes? These ones. So let's look at Dirichlet again. So 0 is u plus at 0t. But now I can express u plus coming from u and v. Okay, so u plus is nothing else than u at 0t plus 1 over gamma v at 0t divided by 2. So if you plug in the definitions for u and v, which we have from here, and then this 1 over gamma takes care of this gamma, and then the sum is u plus and the difference is u minus. So then this is u plus at 0. But now if I make gamma big, gamma goes to infinity, then this term disappears, and we get u at 0t is 0. And this is indeed our classical Dirichlet condition. So now this is the boundary condition for this case. So that's perfect. Classical Dirichlet. And the Neumann case is also interesting. So Neumann boundary condition. So then we have u plus at 0t is equal to u minus at 0t. Right, so that was the perfect reflection condition. And to relate this back, we need to go back to the Cattaneo model. Cattaneo. So here the velocity equation is vt plus gamma square ux is minus mu v. I divide by mu, and then I take the limit directly here. So I get 1 over mu vt plus gamma squared divided by mu ux is minus v. And then I take the limit. Then the first term disappears, and v is proportional to ux. I think I can lift this just a little bit. So then this disappears, and we get d ux is minus v. And now if on the boundary I have v is 0, this means ux is 0. And there's my classical Neumann boundary condition. So then minus dux at 0t is 0. And so also this makes sense. So the hyperbolic Neumann condition is really the Neumann boundary condition for the heat equation as well. Now this correlated random walk is also a good model for chemotaxis. Again, coming back to the measurements. So sometimes in chemotaxis you can measure the particle, how they move. And maybe if there's a signal coming from there, maybe I speed up and go quicker. Or I change direction less often so that I keep the direction going there. So then the speed gamma and the turning rate mu, they depend on the signal. Okay? And so then we get a system of this form. U plus t plus gamma of s u plus x equals minus mu plus s sx u plus mu minus of s sx u minus and u minus t minus gamma of s u minus x is mu plus s sx u plus minus mu minus s sx minus. And now the turning rates also, they got an index plus or minus, because now it depends if I go towards the signal or if I go away. If I go away, I might change right away. If I go towards the signal, I might not change at all. So these rates get indices, they depend on the signal and the gradient. And then also the gamma depends on s. It could also depend on sx. But we have not been able to develop a theory if it depends on the derivative of Sx. So these models were studied by myself and Stevens in 2001, and then by with Rode and Lutscher in 2001 as well. And then, of course, you can do the same thing. So you can do the chemotaxis Cattaneo model, the chemotaxis Telegraph model, the chemotaxis limit. And then if you do the limit, you get the chemotaxis equations. So if you do this here, you get exactly the Keller-Siegel model as it should be. Okay. And then another example is swarming. So this has been done by Ftimi and Stevens and Lutscher. So then you have u plus t plus gamma u plus x equals minus mu plus u plus mu minus u minus u minus t minus gamma u minus x is mu plus u plus minus mu minus u minus. But now these turning rates are non-local. The turning rates now depend on the neighborhood of species. So the idea is fish, for example, if fish build swarms, then they see the fish around them in a certain distance. And so, yeah, I write this down this term. So mu plus minus is then a big function f, which depends on a non-local information, an integral from minus r to r, alpha r u plus minus of x plus minus rt plus beta r of u minus plus of x plus minus rt dr. Okay. And so there's a combined signal, so this u plus minus means you react to species which go in the same direction as you. And then this minus plus indicates you also react of those which are opposing. So if more coming your way than you go, then you might change and go the same way as well. So it looks complicated, it is complicated, it has a non-local term here, which you then put there. But this model has been very successful in explaining all kind of swarms. You can have kind of swarm dynamics, ripples, you can have concentrated swarms, you can have white swarms, etc., etc. So that's how they use it. So, good. So then on this note, I stop this lecture. Everybody's hungry for lunchtime. So then we meet, when do we meet again? 2 o'clock? Okay, 2 o'clock. Thanks.